Good morning students. In previous lecture we have learned about beta spectrum. In that we have concluded that it is the continuous spectrum. And we also learned about neutrino hypothesis. This Paulis adopted this neutron hypothesis in order to overcome the problem faced in the beta spectrum. And he also assumed that in addition to negatron and positron, another particle also emits from the nucleus, which is nothing but neutrino. Antiparticle of neutrino is antineutrino. And so these are the things we have covered in the previous lecture. Today we are going to know about Fermi theory of beta decay. Okay, Fermi theory of beta decay. Today's concept is Fermi theory of beta decay. So when does the neutrino or antineutrino will emit from the nucleus along with the beta particles. Okay, in the process of beta decay, the neutrino or antineutrino will be emitted out of the nucleus. Now today we are going to know about Fermi theory of beta decay. Now, Fermi successfully explained beta decay based on Pauli's neutrino hypothesis. Okay, the physicist Fermi explained well about in detail about the beta decay by considering neutrino hypothesis. Pauli's neutrino hypothesis. So initially in beta spectrum, it is a continuous spectrum at lower energies. It is not supposed to predict the electronic transitions. So again Pauli, to overcome that problem, he has formulated the neutrino hypothesis, and according to that he had made the neutrino and antineutrino to be conserved if some properties are accepted. Okay. Now again after Pauli's neutrino hypothesis, then Fermi he has used the Pauli neutrino hypothesis to explain in detail about the beta decay. Now neutrino hypothesis as well as time dependent perturbation. Time dependent perturbation. So by using Pauli's neutrino hypothesis as well as time dependent perturbation theory, Fermi explained well about the beta decay. Now he has considered the probability that an electron of momentum, okay, the probability that an electron, okay, between the momentum PE and PE plus dPE. Here PE represents the momentum of electron, okay, or electron momentum. So the probability that electron makes the will have the momentum between the PE and PE plus dPE is given by the equation P of PE into dPE. Okay, that means he has given the equation which represents the probability of an electron will possess the momentum between the PE and PE plus dPE. Now that equation is given by P of PE. Here P represents the probability, okay, of electron momentum, is given by 2 pi by h cut mod HIF square dn by dEO. dn by dEO. So the probability that electron possesses momentum between PE and PE plus dPe is given by 2 pi by h cut, okay, mod square HIF into dn by dE naught. Now here we are observing the parameter dn by dE naught, okay, where dn by dE naught represents number of quantum mechanical states, number of quantum mechanical states, quantum mechanical states of the final system, per unit energy interval, So here what is dn by dE naught represents? It represents the number of quantum mechanical states of the final state per unit energy interval. And here you are observing HIF. Okay, HIF is the matrix element which represents the interaction for initial state and final state. Okay, here you are observing HIF. It represents matrix element of the interaction, that means the interaction between initial state and final state. So as we are considering beta decay, that means beta emission, here the initial state is the excited state and final state is the ground state. Okay, so as we are considering beta decay in the sense emission, okay, decay process in the sense emission process. In emission process, where does the emission process takes place? From excited state to ground state. So for any emission process, the initial state is the excited state. And final state is the ground state. This you keep in mind. For absorption, the initial state is the ground state and the excited state is the final state. So as I have said that for any emission process, the initial state is excited state and the lower state is the final state. So here HIF represents the matrix element of the interaction for the initial or final states. Now we are going to define the interaction matrix element. Now we are going to define HIF. So the interaction matrix element is defined as the interaction matrix element. Here what is the interaction matrix element in this equation? HIF. Interaction matrix element is defined as HIF is equal to H suffix, not behind that, okay? HIF suffix. IF should be in the suffix form. It will be, it can be defined as integral psi f star h psi I d tau. Okay, here psi f represents the wave function of final state. Okay, here h is the operator and psi I is the wave function of initial state. That means in beta decay, initial state is the excited state. So the wave function of the excited state represented by psi I. So in beta decay, what is the final state? Ground state. So the wave function of this beta decay represented with psi f. This is psi I. And here H is the operator, which is known as Hamiltonian operator. Here H is nothing but Hamiltonian operator. Hamiltonian operator. Okay, now we are going to consider, we are going to define for beta decay, what will be the final state. So, our concept is Fermi theory of beta decay. Fermi explained well about the beta decay by considering two parameters. What are they? Paulus-Neutrino hypothesis and time-dependent perturbation. And he has given how the electron possesses momentum between one state to another state. And as per he has defined this equation. In this, what does dN by d naught represents? Dn by d naught represents the number of quantum mechanical states. And HIF is the interaction matrix element which tells about the interaction of initial state or final state. And this interaction matrix element is defined as integration of wave function of final state and wave function of initial state. And here psi f represents the wave function of final state. Here final state is nothing but the ground state. And here H you are observing. H is nothing but Hamiltonian operator. And psi I. Here psi I represents the wave function of initial state. In decay process, what is the initial state? I have said that excited state is the initial state for any decay process or emission process. Next, we are going to define psi f. As in the last equation, we have defined the interaction element, that is HIF. In that, HIF is denoted by integral psi f conjugate H psi I into d tau. Here psi f is nothing but wave function, final wave function. H represents Hamiltonian operator, as I have said that. Now, this Hamiltonian operator describes the weak interaction between two states. So, what is the work of this Hamiltonian operator H? This H describes weak interaction between two states. Weak interaction between two states. Okay, and finally d tau we have written. Here d tau is nothing but volume element. D tau represents volume element. Now in decay process, for beta decay, we have the equation n gives rise to P plus minus 1 E0 plus anti-neutrino. And we also considered that psi I. Psi I is nothing but initial state in the beta decay is parent nucleus. It is related to parent nucleus. And psi f. Here f is nothing but final state. Final state in any decay process is the ground state. So, daughter nucleus. Daughter nucleus. Now we are going to define this wave function of daughter nucleus as, that means wave function of final state as defined as psi f is equal to psi f psi e wave function related to anti-neutrino. Okay. Now Fermi suggested a constant, new constant called Fermi coupling constant, and it is denoted by G. So after defining the wave function related to final state, Fermi defined a constant called G. This G is nothing but Fermi coupling constant. G is nothing but Fermi coupling constant. So what is the use of this Fermi coupling constant? It determines the strength of beta interaction. So he considered a constant which is nothing but Fermi coupling constant. So what is the use of this Fermi coupling constant? It describes the interaction of beta interaction, strength of beta interaction. So this G value determines the strength of beta interaction. Strength of beta interaction. Now, by considering the Fermi coupling constant, again the interaction matrix element is denoted by HIF. So, by considering the Fermi coupling constant, again the interaction matrix element is written as HIF is equal to G, okay, integral psi f star conjugate psi e conjugate psi neutrino into m psi I d tau. You know what is psi f, psi e? That means psi e represents electron wave function, psi nu represents neutrino wave function. Okay, psi I represents the wave function of initial state, d tau represents the volume element. You know each and every parameter. Now here m we have used new term. Okay, this m is dimensionless matrix element, which is an operator. As similar to H, it is also, m is also an operator, which is dimensionless. Okay, which is dimensionless. Now, since the neutrino interaction is weakly with the, okay, when compared to positron and negatron, this neutrino interacts weakly with the nucleons, because if you consider positron is having positive, it is a positively charged particle. If you consider negatron, it is negatively charged particle. Okay, beta minus. Whereas neutron, I have said that it is a neutral particle. So as it is a neutral particle, it has less interaction with the nucleus. So due to the neutrino weak interaction with the nucleus, we can assume that neutrino waves are unperturbed by the nuclear potential or nuclear reactions, and we can consider the interaction of neutrino as a plane wave with a propagation constant k, and it is given as k is equal to p nu by h cut. Here p nu represents the that means neutrino propagation. It's neutrino plane wave of the neutrino, and here k represents the propagation constant. As we know that wave function for neutrino is denoted by psi nu is equal to v power minus 1 by 2 exponential of minus I by h cut p nu into r. Okay, here now we are going to consider for high velocity electrons, the wave function can be written as, okay, so this is for the, as neutrino interaction is less with the nucleus and it acts as a unperturbed, okay, we can consider it as a unperturbed wave function. So the wave function of neutrino is given by this. As electrons possess high velocity, then the wave function of electrons can be known by the equation sin E is equal to v power minus 1 by 2 v power minus 1 by 2 exponential of minus of I by h cut Okay, PE into R. So this is the wave function of neutrino, and this equation represents the wave function of electron. Now here V, we are saying here V is the whole volume. Okay, here V represents the volume. V represents the volume. Now we are going to consider this by assuming the plane wave for the wave function of electron and neutrino and neglecting their interactions with the nuclei. Then the matrix element we are going to write as, so far we have considered the matrix element which tells about the interaction. Now what we are going to do is, let P nu and Pe are the momentum of neutrino and electron, P nu and Pe. So here P nu represents the momentum of neutrino. And what is Pe represents? Momentum of electron. Now by considering the two parameters P nu and Pe, and we are saying that both represents the momentum of neutrino and momentum of electron respectively, and R is the position coordinate. Here let R, and here also we have used the R parameter. It represents the position coordinate. Now we are assuming that the plane wave for the wave function of electron and neutrino, and neglecting their possible interactions with the nucleus. Now that means we are assuming that both possess the plane wave function, and if you consider the interaction with the nucleus, you will get the complex wave function. What we are doing is, we are neglecting the interaction of neutrino and electron with the nucleus, okay, as a plane wave function. That means we are not considering the interaction of neutrino and electron with the nucleus. Then we are going to define this interaction matrix element as, by neglecting the interaction of electron and neutrino with the nucleus, then the interaction element HIF is defined as, HIF is equal to G integral psi f conjugate 1 by V exponential of minus I by H cut into Pe plus P nu into R into M psi I d tau. Now we are going to express the equation for the allowed transition. That means if interaction is there, then so without the interaction with the nucleus for electron and neutrino, the interaction element is defined by this equation. If you assume the interaction is possible with the electron and neutron, that means the interaction of electron and neutrino with the nucleus, then the allowed transitions of matrix interaction element is given by HIF is equal to G by V integral psi f conjugate M psi I into d tau. That is equal to G by V MI F. Okay, G by V mod MIF. Here mod MIF is nothing but overlap integral. This one, overlap integral. Now we are going to consider, we are going to derive statistical factor. Here statistical factor in the sense dn by de naught is the statistical factor. Here dn by de naught is nothing but statistical factors. or you can say it as final state density. Okay, final state density. Now, so to find this, an electron and a neutron are independent of one another, hence the number of states available to them jointly is given by. So, both the electron and neutron are independent. Okay, if you join their interaction together, okay, then the density of states is jointly expressed as dn is equal to 4 pi v pe square dpe by h cube into 4 pi v p nu square dp nu by h cube. So jointly we are going to consider the number of available states for electron and neutrino. Now the number of states per unit energy, that means number of states represents this equation. Per unit energy is denoted by dE naught. So dN by dE naught is given by multiplying just. You will get 16, okay, I square V square by H to the power of 6 into Pe square P nu square dPe dP nu by dE naught. So just I have multiplied these two things, then we got. Now the total available energy states are E naught is equal to energy for the neutrino, energy of electron. So this the sum of energy levels of neutrino and energy levels of electron gives the total available states in the nucleus. So for a fixed electron we have dE naught is equal to dE nu. Now we are going to consider the momentum Pe, okay, electron momentum and momentum of neutrino are related to energy equation, which is given by, here energy equation is denoted by E square is equal to, energy equation for electron and neutrino we will represent separately. So energy equation for electron is denoted by Pe square C square plus M square C to the power of 4, and energy equation for neutrino is E nu is equal to E P nu. Okay, now we are going to consider, from this you can consider dE nu is equal to, okay, Cp Cd P nu. Okay, differentiation of this. Now using these equations, okay, like using E naught, dE naught, okay, P square, P nu and dE naught equation, then we are going to define this dN by dE naught. So by substituting all the derived equations in the equation, dN by dE naught, we will get dN by dE naught is equal to 16 pi square V square by H to the power of 6 into Pe square of E naught minus E naught by E whole square into dPe into dE nu by C into 1 by dE nu. Okay, now here by inserting the statistical factor, okay, dN by dE naught from and HIF in equation 1. So we are going to substitute dN by dE naught we have derived, as well as HIF factor also we have derived. Now we are going to substitute HIF equation and dN by dE naught equation in equation 1, that is initial equation. HIF is equal to that is P of PE plus dPE is there. In that equation we have to substitute. So what you will get? P of PE into dPE is equal to 2 pi G square by H cut V square mod MIF square into 16 pi square V square by E cube H to the power of 6 PE square into E naught minus EE square into dBE. So by substituting, that means by inserting this statistical factor and HIF into equation 1, then we will get the probability term as this equation. And the overall, the probability term is given by P of PE plus dPE is equal to G square. Okay, that means after simplification we will get G square MIF square by 2 pi cube C cube H to the power of 7. That means by simplifying this equation we are going to get finally P of PE dPE is equal to G square mod square MIF by 2 pi square E cube H cut 7 into E naught minus EE whole square into PE square and dPE. So this is the probability that electron possesses the momentum. So this is about the Fermi theory of beta decay. Thank you.